Evening once again. We're going to have a quick in-depth look at the measurement system, each of the different sections. We have, for instance, the more in-depth measurement systems handout, number 4 this particular one is. Mainly based around where the introduction was, leading on to a little bit more information. Very well, don't worry. So there's also that PowerPoint, have it, or a Word document, have a wee quick read. Just going to scan through 5, 6, 7 and 8 this time. So the 4 stages: the sensing element, signal conditioning, signal processing and data presentation. The 4 main sections of a measurement system. Have a quick read. They're only not terribly far, or not too much typing on each of them, so don't worry too much about them. Have a quick read through them, and again, we're not overly looking for the really in-depth detail each time here. We're really looking for an understanding and appreciation. So some of the notes you see here are probably too in-depth for what we really need, but it's just good to have a real background overview of everything that we do have. So as seen as the measurement system's introduction, sensors are essential to the measurement system. They're in contact with the process that's being monitored and act as the feelers, for instance, for the measurement system. Sensor is the device which usually possesses a characteristic dependent on the variable being measured. For instance, a thermistor, which is a combination of thermal and resistor, is a type of resistor which resistance changes noticeably with temperature. Right, this characteristic makes the thermistor an ideal temperature sensor. Okay, and there's other ones here as well. We'll go down through. There's a type of things for flow measurement, and there's different types of one: elbow flow meter, orifice plate. So that there was in your practice one from the previous lecture, and a quick description of some of what these are as well on the right hand side. So you can have a quick read through of these. It's be worthwhile just making sure you know at least 1 or 2 per area. Know the different types of things that can be measured: capacitive, resistive, magnetic, piezoelectric, strain, optical, and so on. Just be able to rhyme off a couple of those in case you're asked for different types of measurement systems, for instance. And a very quick conclusion there as well. Signal conditioning, as I say, these are all very brief introductions to each of the 4 characteristic settings. So just quick read over. And again, a bit of an introduction, tells you a wee bit more in depth that we're not overly concerned with. Just remember, we're not delving over the details. Now, do not be worrying about this type of diagram. You're not going to ask to be replicating it. You're not even going to be able to properly be asked to explain much about it other than what an amplifier is. The base knowledge of each of these components, what they do, how they affect this system, is what we're talking about here. Okay, different types of filters: low pass, high pass, band pass, band stop. And again, you're not going to be asked to reproduce any of these, don't worry that way. But you might be asked about different types of filters and why you might use a low pass filter over a high pass filter, for instance. There's also signal processing and obviously the final one, data presentation. Again, not overly long, to have a quick read through them, to have appreciation of the different type of things that are actually involved within the steps. Okay, so the signal processing, for instance, PIC microcontroller, for instance, and so on. Right, we're not overly concerned about the overall detail, just being able to name and recognize what each stage could be used for. Right. And again, data presentation, only a page long. Have a quick read and have an appreciation of what we're talking about when we say about a data presentation. Moving on to another section, it's number 9 from the Word documents, the characteristics of a measurement system. So this is one where it'd be good to make sure you're able to distinguish different types of characteristics and what they are. So if you're told, for instance, what a range is, can you describe to me within a short sentence what range is and what the difference is between the likes of range and span? How do they differ? So brief introduction here, just categorizing what we're talking about to start off with. And we've got generalized model of a system, and again, don't worry too much. This is the more slightly complex version, showing you all the calculations and math behind the mathematical modeling of a system that we're not overly concerned with right now. skip on down, and this is the bits here. I know they're a wee bit grainy. Unfortunately, they didn't come up exactly great from the notes I was taking them from, but you should be able to read them pretty well. So the range is, given a measurement system, the range is defined for the input as the interval from I minimum to I max, and for the output is O minimum to O max. So the range is between what it can measure between and what it can output between. So for instance, it might be able to measure, for instance, between 0 and 100 degrees Celsius. Okay, it might be a voltage it's measuring in, it could be a resistance, it could be multiple things, and it's given from something to something else, either input or output wise. The span is slightly different in that it is the maximum variation of either input or output. So it's I max minus I min, or O max minus O min. So it's one value, where range is two values from something to something, so from X to Y, for instance, where span is just Z. It's just a standard answer of what the span is, which doesn't really give you a comprehensive view of exactly what the sensing element, for instance, is actually capable of. Linearity is basically the measurement system that is the relationship between I and O. So if the relationship between I and O is, one second. Okay, back again. Where do we get to? Linearity, I think we just finished. Where it's the relationship between I and O, where the output according to the input minus, for instance, a constant of I plus I think the that would be the offset. So the output of I is equal to, that is actually the K of I, so constant multiplied by whatever the input is, minus or plus basically the y-intercept, that would be, you maybe know that as, which is obviously a linearity or linear relationship. There's obviously non-linearity as well, which is the relationship between O and I, gain, output and input, where O of I is equal to Ki plus A plus N of I, where N of I is a non-linear function, which could be, for instance, exponential of the input to the system. So moving on down, as I say, we have non-linearity as displayed with the red line here. So we have our input along our x-axis and our output on our y-axis. So we have O of I from the previous one is equal to Ki plus A minus the N of I, where N is the non-linearity multiplication constant. So if our linearity scale here is sort of rising here to 45-degree angle almost, is the linearity one, it's the ideal characteristic that you want, but what you actually achieve is the red one here, the real characteristic, which is a non-linearity. So again, we're not overly concerned about the formula or anything here about full-scale deflection or anything like that. What we're really looking to be able to do is describe what non-linearity is and maybe graph a very quick description of what non-linearity would be. Well, we've got sensitivity, which is the rate of change of the output of an element with respect to the input. Okay, so how quickly something changes is how sensitive it is. Environmental effects, there's a few different ones. There's two things, two sort of categories to fall into: interfering input and the modifying input. One changes the gradient or the slope, which is the modifying input, and then there's the environmental interfering one, which changes the intercept point of your chart. Hysteresis, you should hopefully know what hysteresis is. You've maybe come across it before, I would have thought. Occurs when output takes two different values for the same value of input, and this would, and generally is described as when it's rising. For instance, if you say the temperature is rising, it gives out a, say, let's go with a resistance here. So your linearity ideal constant here is the dashed line that you see. If the real constant here is the blue line of the hysteresis, so as the temperature rises, the resistance is going kind of slow and produces this point here at I1, which is output I1 underscore 1. And on the way back down, so say for instance the room temperature rises up to, say, 50 degrees for instance, and as it comes back down again at the exact same point of input, so let's say it's a temperature of, who cares, 25 degrees for instance, it's going to give a different output up here. Okay, so as it rose to 25 degrees, it gave this particular output, the blue one. As it dropped to 25 degrees, it would have given that particular output. So the hysteresis is basically the difference, the gap between these two inputs, between the two outputs on the same input. Resolution, so the system of a measurement element may increase in discrete steps in response to the continuous increase of an input. And basically the change in the input resolution is the widest input step for which there's no change in the output. You should remember that from your PLC days. Then the resolution can be expressed as a percentage of full scale deflection, which we're not overly concerned about the formula, just being able to recognize what resolution is. There's also wear and aging, error bands, because basically manufacturers do not, one, want to, and two, maybe are able to on a appropriate scale, are able to give every last one of these, for instance, wear and ages, resolution errors, environmental effect errors, all of these, what they do is they group them together and call it the error band. And the idea is that the probability of an output occurring within that error band should be 100%. So the nonlinearity, hysteresis, resolution effects in modern sensors are usually so small that it is difficult to quantify them separately. Manufacturers define instead the performance of the elements in terms of error bands. So basically how far above and below that perfect linearity there does all the measurements where they should fall is called the error band. So the exact or systematic statement of performance is replaced by a statistical statement in terms of probability density function, and you can chart that out as well if you really wish. We're not concerned with it now; it's sort of a bit more advanced, but being able to state what the error band is a critical thing that we're possibly looking. And again, being able to show the chart, show what an error band is what we're sort of aiming towards, not being able to draw the characteristic response or anything like that. There's also the dynamic characteristic of measurement systems. Have a quick read. Again, more an appreciation we're looking for here rather than a real in-depth understanding. And again, a couple of elements to finish off with we're not overly as concerned with, but what we are more concerned with is being able to recognize each of these different system characteristics and being able to describe them effectively enough. If posed a question, for instance, describe range and draw a chart to describe it. Okay, describe what nonlinearity is in relationship to a sensor. These type of things. Just back to the main folder here, there's also supplementary material. If I hadn't said in the first one, 16, 18, 19 and 20, slightly more long-winded if you're completely bored and you want to read some extra background information in case you don't know, for instance, of a particular type of sensor. There's bits copied out from textbooks here, being able to give you a better understanding, hopefully, of each of, what's wrong with that? Yeah, close all tabs. Of sensors, actuators and so on, all the way through each of those. So folks, I think we'll end that one there. We've covered now pretty much all of these Word documents, talked about some of the PDFs, went through examples. I said about the extra, just refresh here, I said about the extra PDFs that I have available for you, extra background information reading if you so wish, if you need extra background information, that is. There's also stepper motors there, just a couple of PDFs, nothing overly serious. But all there, ready to get cracking on with, and this is where the majority of your marks are pretty much going to be coming from for your exam. As I said before in the previous video that is, there's also the introduction, being able to describe what mechatronics is, various definitions, there's various systems all described in there, being able to talk about the mesh diagram, understanding what the four or sometimes 3 elements of mechatronics are. In this case, this particular one describes it as control systems engineering, electronic systems engineering, mechanical systems engineering, and computers. And all 4 together would give you mechatronics engineering. Obviously, you start to break down the other 2 ones here. So control systems and computers would give you digital control systems. This is what this one's talking about in this particular one. So all 4 together, mechatronics. Yeah. Okay. So make sure you're able to look over and be able to quote off some of the stuff there.